Dear students, let us begin our session with the rest of the portions from second module. So this is the syllabus of second module. As you all know, we have covered the basic program execution registers in the last session. So in this session, we'll be moving with operand addressing and the concepts of multicore architectures and the various power reduction techniques in processors. The first topic is operand addressing. In Intel 32 architecture, machine instructions operates on operands with more than either 0, 1 or 2 or more. And these operands can be either addresses, registers or immediate values. So what is an operand? An operand is a data that an instruction can work on. For example, consider the case of move EAX5. Consider this as one operation. You can see the operands. What are the operands here? One operand is EAX, that is extended accumulator register, and another operand is the immediate value 5, right? So actually move destination comma source. You all have studied coding with 8086, right? So this is one such basic instruction which we took to explain operand addressing. So move EAX comma 5 indicates like the operands are the destination is EAX and source as the 5, which is the immediate value. The value 5 is being stored in this destination. Some operands are specified explicitly in the instruction while the others are implicit, meaning they are implied by the instruction itself and not written out in the code. That means certain operations are being written out in the code in the form of registers, immediate values or memory addresses, and certain other operands they are not shown in the instruction but they are implied by the operation, and the CPU knows to use them by default based on the instruction's behavior. The data for a source operand can be located in either the instruction itself, which is an immediate operand, which we already seen with the example move EAX, 5. Either it can be in the register or in the memory location or an IO port. Whenever an instruction returns data to a destination operand, it can be returned to either a register, a memory location, or an IO port. Coming to the immediate operands. So immediate operands are constants embedded directly in the instruction itself, and they serve as source operands in instructions. Immediate operands are always read-only, used as values and not addresses or destinations. For example, add EX, 14. It adds 14, which is the immediate value, to EAX. Almost all arithmetic instructions support this immediate operations, and there is one exception: division and IDIV do not accept this immediate operation. Rest of the operations like addition, subtraction, multiplication, these all things support this immediate operands. And in the case of immediate operands, the maximum value allowed, it can never be greater than the maximum value of unsigned double word integer, which is of 2 raised to 32. And a double word, what is meant by a double word integer? It is nothing but it is a D word. We know that in Intel, one word is equal to 16 bits, right? So double word in that case, it is 2 into one word. That is 2 into 60. That is equal to 32 bits. Next is the register operands. Here the source and destination operands can be any of the following register, depends on the instruction being executed. It can be either in a 32-bit general purpose register like this, or a 16-bit general purpose register, or an 8-bit general purpose registers. And it can be either segment register, E flag register, or 87 FPU register, MMX register, XMM register, these are all multimedia registers. Control registers, debug registers, MSR registers. So this register operand can be one among any of this. Similarly, for the register operands in 64-bit mode, here also the 64-bit mode register operand can be any of the following registers which is shown here. Okay, so next comes the memory operands. Here in memory operands, the source and destination operands in memory are referenced by means of a segment register and an offset. Segment registers specify the segment containing the operand and offsets specify the linear or effective address of the operand. Normally, offset can be 32-bit or 16-bit and the memory operand structure is shown here. So I have already mentioned like offset can be 32-bit. Offset means it contains the linear address that is 0 to 31 altogether 32 bits. And segment register it is of 16 bits. It can be either 32-bit or 16-bit. In the case of memory operands in 64-bit, so here a memory operand can be referenced by a segment register as well as an offset register as in the 32-bit. Here also the offset can be either 16, otherwise 32 or 64-bit. Here I have shown a figure regarding 64-bit. So it can be either 16, otherwise 32 or 64-bit. Okay. But in the previous case, the offset of 32-bit mode, the corresponding offset of the linear address can be either 16 or 32-bit. Okay. Now specifying a segment selector. The segment selector can be specified either implicitly or explicitly. The most common method of specifying a segment selector is to load it in a segment register and then allow the processor to select the register implicitly, depending on the type of operation being performed. Now, the default selection rule for segment register is shown here in this figure. Here, the reference type is instruction. Here, the register used is CS, that is the code segment. Here, the selection rule is like all instruction fetches using this particular register. While using the register stack segment, all stack pushes and pops has been performed and any memory reference which uses ESP or EBP register as the base register. And when it comes to the DS data segment, here all data references except when relative to stack or string destination is done. And when it comes to the destination string, that is the ES, here destination of string instructions is being executed. So coming to the segmentation in 64-bit mode, here majorly there are two modes are there. Depends on whether the CPU runs behavior of CPU, whether it runs in compatibility mode or in 64-bit mode. If it is in compatibility mode, segmentation works like legacy IA32 mode. If it is in 64-bit mode, segmentation is mostly disabled. Now coming to the flat address space, in 64-bit mode, segmentation is disabled for most segment registers and the base address is treated as 0, so the linear address is equal to the effective address. And there are certain exceptions in the case of FS and GS which retains the base address. And these are the excess registers that is used in segmentation and can be used as an additional base registers for certain address calculation. Next heading, specifying an offset. So how an offset is being specified? The offset part of the memory address can be specified directly as a static value or through an address computation made up of one of the following components, either displacement, base, index or scale factor. Displacement means it can be either a 8-bit, 16-bit, 32-bit value. Base, it indicates the value of general purpose register. Index, it indicates the value in a general purpose register. And scale factor, it multiplies the index and the allowed values are 2, 4, or 8. And the offset that resulted from adding these components which I mentioned earlier is known as effective address. So that includes the base, index, scale factor, displacement, all these things. And each of these components can have either a positive or negative value with the exception of the scale factor. And this is how this figure shows how an effective index address or offset is computed. So this is offset is equal to base plus index into scale plus displacement. So based on this, effective address of the or the offset is being calculated. Coming to the addressing modes and the common use cases, here it can be either displacement only, that means direct or static memory access. Example, move AX in square bracket 1000. Base only, that is dynamic addressing using pointers. So this is one such example of dynamic address using pointers. Another type of addressing mode is base plus displacement. So it accesses record fields or procedure parameters. So example here, it's shown here. So this is 4 is the displacement. We will be giving a base plus displacement. Next one, index into scale plus displacement. So this is another type of addressing mode. It is efficient array indexing mode. So example, you can see index into array plus corresponding index into scale plus displacement. Then comes the base plus index plus displacement. It is one of the multi-dimensional arrays or structure arrays, and the corresponding example is shown here. And when it comes to the base plus index into scale plus displacement, it is one such complex array and is normally a 2D arrays, and the example is shown here. So these all shows the various addressing modes and the common use cases that is being used here. So coming to this specifying an offset in 64-bit mode. So here also in 64-bit mode, the offset part of the memory is in 64-bit. Over there it was in 32-bit. So here also the various components that is used to address the computation of this offset in 64-bit mode are same only, displacement, base index and scale factor. Only thing is like here we are having a 64-bit reference, and here one apart from the previous addressing modes which we described. So here one more addressing mode is there. A new addressing mode is there, that is the RIP plus displacement, where RIP stands for instruction pointer register plus displacement, which enables RIP relative addressing, that is position independent code, and is commonly used in shared libraries and modern compilers. An example for such an addressing mode, RIP plus displacement, is shown here. Next one, assembler and compiler addressing mode. At the machine code level, the selected combination of displacement, base registers, index registers, and scale factors is encoded in an instruction. All assemblers permits a programmer to use only any of the allowable combinations of addressing components to address operands. I/O port addressing. The processor supports I/O address space that contains up to 65536 8 I/O ports, and the ports can be that are 16-bit and 32-bit may be defined as the I/O address space. An input-output port can be addressed with either an immediate operand or a value in the DX register. So next topic is multi-core processor. So what is a multi-core processor? It is a single computing component with two or more independent processing processors, and each core can execute instruction independently. And now what are the key features? So first one is parallelism. So it can independent execution. It can do execution parallelly. Throughput, that means higher performance with lower clock speeds per core. So it improving the overall throughput. Share resources. The cores can be shared the cache memory controllers, buses, etc. can be shared. Scalability is there. Then scheduling is there. OS distributes task equals various available cores for efficiency. So next heading, power reduction techniques in processors. So what are the various power reduction techniques that is available in processors? First one is dynamic voltage and frequency scale. So which adjusts the voltage and frequency based on workload, and it lowers the power consumption when performance is not needed. So we know that power is directly proportional to V square into F. Thus whenever we tries to reduce the voltage, it drastically saves power because it is square root of voltage. So it is power is square of voltage. Whenever we try to reduce this, power will also reduce, right? Now next is the power gating. So in certain cases there can arise like certain portion of the uh, unused core may not be working in a chip. So those portions can be shut down or turn off, uh, can be turned off. So this turning off the entire blocks of the chip, that is unused core or functional unit, is known as power gating. What happens? It prevents leakage power in the idle part of the chip. Next one, clock gating. So similarly, we'll disable clock signal to inactive components. Here also we can reduce the dynamic power by stopping unnecessary switching activity. Next is the multiple threshold voltage. So design transistors with higher threshold voltage in certain non-critical path in order to reduce leakage. So here we are developing different transistors with different threshold voltage. So based on the requirement, certain transistors will be on and certain will be off. So what happens ultimately? So inactive components will be off and the power consumption reduces and the speed increases. Next one, low power idle states. Processors enter deeper sleep states when idle. What happens? It also saves power by shutting down internal components. Next is NTC, near threshold computing, that operates transistor at voltage just above the threshold voltage, so thereby reducing the energy consumption. And last one is 3D chip stacking with TSP, which reduces the wire length, communication power between the components, and can help isolate heat and improve the power delivery. So these are the various power reduction techniques that is available in multi-core processors.